Thad, we've covered a lot of different machine learning algorithms, but what about situations where we have time series?
You mean like speech recognition?
Yeah, I know you've worked in sign language recognition and handwriting recognition. They seem to be similar problems.
Yep, they are. Pattern recognition through time is one of my specialties, and is where the AI community has made a lot of progress. When you think about it, pattern recognition through time should be easier than situations where you have just one measurement.
You mean like how face recognition is easier when you have a video of a person as opposed to a single photo? If one particular frame of the video is badly lit or the person is looking away, the next frame might be better.
Precisely. But in this section, we are going to focus on situations where there's a language-like structure to the problem. In other words, there is some fundamental unit, like a phoneme in speech or a letter in handwriting, that is combined with other units to make bigger constructs like words, which are then combined in even larger structures like sentences.
So, besides speech, sign language, and handwriting, what other problems have this same sort of structure?
Well, in my opinion, most human activities through time have a language-like structure. Playing basketball, driving a car, or even just vacuuming the floor all seem to have fundamental units of movement, combinations of those movements, and a sort of statistical grammar. I believe this area of AI is one of the most promising for future research, and I'm excited to share my knowledge of the subject.
I know we're going to cover dynamic time warp and hidden Markov models in this section. Where should we start?
Well, let's start with a challenge question on HMMs that gives a preview of what we're going to be learning. Let's start with a problem I'm currently exploring, dolphin communication. Here's a spectrogram of a dolphin whistle. In actuality, dolphins have several types of vocalizations, including burst pulses and echolocation. But whistles are the easiest to see in a spectrogram.
First, let's talk about what a spectrogram is. On this spectrogram, the x-axis is time, and the y-axis is frequency. The brightness of the pixels indicate the amount of power in that frequency band.
Since we are recording in the ocean, there's a lot of noise in the lower frequencies. 5 kHz and lower tends to have a lot of boat and wave noise. However, the whistles of the Atlantic spotted dolphin tend to range from 5 kHz to 17 kHz. These whistles can be heard up to 3 miles away underwater.
Why do they whistle?
Probably for a lot of reasons. But one thing we do know is that dolphins have signature whistles that act much like our names. If a dolphin enters a new area and feels like company, it whistles its signature whistle, which helps its friends know where it is and how to find it.
So what are we seeing in this spectrogram?
To me, it looks like the same whistle repeated twice. The whistle has 2 parts. Our task is to be able to recognize classes of whistles so that our marine mammal researchers can automatically annotate their database of recordings.
Well, I see one problem already. The second time the whistle is repeated, it seems a little more drawn out.
That problem is going to be the focus for this lesson. We need to be able to handle classes of signals where each example may be warped in time a bit differently.
Okay. Well, for features, can we just use the whistle frequencies through time?
Normally that would be a good idea, but in practice, the dolphins often raise or lower the basic frequency of the whistle. What seems to matter is the pattern of relative rises and falls of the whistle through time.
In that case, let's use delta frequency. Here, instead of 5, 14, 10, 7, 10, and 14 kilohertz, let's use 9, -4, -3, 3, and 4.
That will help our recognizer handle the whistles no matter what frequency they start at. Next, let's work on the time warping.
Just to be clear, you're talking about the problem where I could draw out your name, saying Thad, or say your name quickly, like Thad.
Yep, that's precisely the problem we have. But with dolphin whistles, the problem is easy to see in the spectrogram. Basically, we need to match the features that make the whistle distinct, no matter if they are drawn out or produced quickly.
Well, you always say do the simple thing first and add intelligence only if necessary. What happens if we just do Euclidean distance here?
Let's try it and find out. Here are some reasonable delta frequency numbers for the top and bottom graphs.
The top time series has 21 samples, but the bottom one only has 12.
So how do we do a Euclidean distance?
Well, a simple thing to do is pad the bottom one with zeros.
That's reasonable. Other options would be to fill in with the average value or the last value, but any of these options will work for our example.
Okay, well now we can figure out the Euclidean distance by simply doing the square root of the squares of the differences. Let's see. 0 minus 0 squared is 0. 0 minus 5 squared is 25.
And 2 minus 5 squared is 9. and 3 minus 5 squared is 4.
And so on. Doing the math, we get the square root of 170, which is approximately 13.
Yep, now let's try using dynamic time warping to do the same problem.
Okay, so all dynamic time warping is doing is trying to align the samples between two whistles we are comparing so that they best match up.
Yep, let's line up the two signals we are trying to compare on the x and y axes. That will allow us to more easily see how we are matching the samples.
Okay, let's put the shorter one on the y-axis for convenience.
A match without any time warping would be a straight diagonal going from the lower left-hand corner to the upper right. But for the types of signals we are comparing, that would be rare.
We know we have to start with the first sample in each signal. In this case, they are both 0.
For the next sample on the x-axis, we have another 0. Is it better to stay matched to the 0 in the shorter sequence or transition to the 5 in the next sample?
Well, there will be less difference if we stay with the 0.
So we'll draw a horizontal line here, indicating that we're matching the first two O's on the x-axis with the first O on the y-axis.
For the next sample, we have a 2. That still matches with the 0 better than the 5.
So we continue the horizontal line.
But then we get a 3 on the x-axis, which matches the 5 better.
So we transition up 1 on the y-axis to indicate that.
We're going to have several 3s in a row next on the x-axis. How do we match them to the 5s on the y-axis?
Well, we're going to need to transition to the 2 and 0 on the y-axis soon. So let's make our transitions so as to keep as close to the diagonal line as possible.
Oh, I get it. We're trying to match the values as closely as possible to minimize the error, and if the values otherwise tie, we try to keep to the diagonal.
Correct. The 3s will match the 5s pretty well. And by the time we get to the 2, the 3 matches that even better. When we get to the 2 and the 1 on the x-axis, it'll match very well with the 2 and 0 up here. And the 0 and -1 match the 0 pretty well.
Then we can match the -2, -3, -3, and -1 sequence on the x-axis to the 3 -3s on the y-axis.
And the rest of the long sequence, 0, 1, 1, 1, 1, matches the 1, 1, and 2 on the y-axis. The last 1 has to match the last 2 to finish the process.
Now we can calculate the Euclidean distance as before, but this time we have better matches.
Yep. Writing it out, we have the distance being the square root of 0 minus 0 squared, which is 0, plus 0 minus 0 squared again, which is again 0, 2 minus 0 squared, which is 4, 3 minus 5 squared, which is 4.
I think we get the idea.
Sorry, I always have to see these things written out to really understand them. After a lot of scribbling, we get a distance of the square root of 34, which is approximately equal to 6.
That is less than half of the distance we calculated before when we just padded the shorter sequence with zeros.
Which shows the power of dynamic time warping. For situations where we know the signals we are comparing will have some sections that are faster and some sections that are slower compared to each other, DTW is a very useful tool.
I see a problem, though.
What's that?
Let's suppose we have two signals that really are not that similar. Dynamic time warping could allow them to match much better than they should. Look at this example where we use a different shorter signal, along with the same long one as in the last example.
Okay.
While I have to start by matching the 0 and the 3, I can match the first half of the x-axis sequence to the 3 so that I can get to the negative section of the sequence to get a better match. Then I'm in a positive section of both sequences again.
Yep, that can be a problem. In this case, the distance is poor because of all those numbers at the first part of the sequence, matching the 3. But the severe amount of warping we're allowing means that the distance is probably smaller than we'd like.
One way we could force a more reasonable matching is to bound how much we're allowed to deviate from the diagonal.
Yep, we can use Sakaue-Chiba bounds to force more reasonable matches.
Sakaue-Chiba? Now you're just making things up.
No, really. It says we won't allow matches outside the limits placed by these diagonal lines.
That will cause the matches to be worse, leading to a bigger distance.
Which is what we want.
How do we calculate these bounds?
Often empirically. We set different bounds and use cross-validation to make sure they are reasonable.
Well, what if some sections of the signal should have different bounds than others?
Like on our example, this section here might have a lot of variance, being short or long, but the hump may have less variability in its shape.
And perhaps the last section can then have more variability again. Basically, there are 3 sections of the signal, and each can have a different amount of allowed warping.
We could try to have different Sakaue-Chiba bounds for each section of the signal.
True, but that seems complicated to train, and I know you prefer hidden Markov models for such problems. Why don't you introduce them?
Okay, you know they're my favorite technique. Hidden Markov models, or HMMs as they are known to their friends, are a useful tool for looking at pattern recognition through time. They're similar to other Markov models in that they have states that represent a set of observed phenomena and a set of transitions that describe how we can move from one state to another. We'll be considering first-order Markov models, which only depend on the state immediately preceding them and not a history of states. Hidden Markov models are a variant that are used for recognition of many types of signals that have a language-like structure.
So what's hidden about them?
With HMMs, we don't necessarily know which state matches which physical event. Instead, each state can yield certain outputs. We observe the output over time and determine a sequence of states based on how likely they were to produce that output.
Okay, I see. So since HMMs encode sequences over time, we could use them for recognizing things like speech, handwriting, or gestures.
Exactly. And HMM researchers have spent decades figuring out tricks like state tiling, context, stochastic grammars, and boosting to improve performance. In this lecture, we'll start with how to decode an HMM, where we calculate which model best fits a sequence of data.
We should probably go over how to represent an HMM.
Right. The Russell and Norvig book draws them like a Markov chain and adds an output node for each state. In this representation, which is common in the machine learning community, each x sub I represents a frame of data. X sub O is the beginning state that is useful for bookkeeping later. X sub 1 represents the first time frame, t equals 1. E sub 1 represents the output at that time. X sub 2 is the next time frame, and E sub 2 is the output at that time, and so on until we get to the end of the sequence. The HMM states are implicit in this representation. However, I find it easier to think of HMMs in terms of their states, so I'm going to deviate from the book and use a representation that is more specific to HMMs for this discussion. To get things started, let's imagine we have a signal through time that looks like this graph. At t equals 0, its value is -2. By t equals 10, it is at -1. By t equals 15, it's at 0, and at t equals 35, it's at 1. At t equals 38, it's at 2.
So it looks like the graph is made up of 4 different parts.
That's right. We're going to use a 4-state HMM to represent it. We are trying to design a model that could have generated this data. In this case, we are going to use a left-right HMM, meaning that we never transition back to a previous state once we've left it. These loops are called self-transitions, which indicates that the model can stay in the same state for several time frames.
Next, we need to figure out the emission probabilities.
I like to call them output probabilities, but it's just a different name for them. All it means is which values that are allowable while we are in a given state.
It's a little bit more subtle than that, right? Since the output distributions are densities, these are not really probabilities.
But it's a convenient fiction for our discussion, so I'm going to stay with it. In this case, creating the output probabilities is easy. The first part of the graph is from -2 to -1.
And all values are equally represented, so we can just use a boxcar distribution.
Great. For state 2, the output distribution is going to be a boxcar from -1 to 0.
And state 3, we have a boxcar from 0 to 1. And state 4, it is from 1 to 2.
Now we need to figure out the values for the transition probabilities. Let's look at the first part of the graph again. We spend about 10 time frames in the first part of the graph before we transition to the second part of the graph. So we want to assign an appropriate probability here, where we escape state 1.
Well, that seems simple enough. Let's assign a probability of 0.1. That way, on average, we expect to stay in that state for 10 frames.
Since all the probabilities out of a state have to sum to 1, and we only have the self-transition probability left, we know that it has to be 0.9.
And here's a little trick. If we want to know the number of time frames we expect to stay in a given state, we can just use the formula 1 over 1 minus the self-transition probability to figure it out.
Thanks. For some reason, I keep forgetting to use that trick when I'm working on more complex HMMs where there are a lot of transitions out of a state.
We can continue this process for each of the states. State 2 has 5 frames, so we'll make this output probability 1/5 or 0.2, and this one 4/5 or 0.8. State 3 has 20 frames, so this arrow gets a 1/20th or 0.05, and this is 0.95. And the last transition out of the model is 1/3 or 0.33, with the self-transition being 0.67.
Hold it, I just realized something. You said I could figure out how many frames I expect to be in a state by using the formula 1 over 1 minus the self-transition probability. But if I set the probability to 0, I get 1 over 1 minus 0, which equals 1. So that means I'll get at least one output from that state.
But that's fine. We output as soon as we enter the state from the previous state, and then we transition to the next state.
Okay. That explains something else to me. A lot of manuals and toolkits put a dummy state at the beginning of each model, I guess to explicitly represent entering the first state. Actually, that leads me to another point. When I'm being more formal, I just put the arrow at the first state. If we can enter the model at several different positions with equal probability, I put these arrows at each potential point of entry. If the entry points have different probabilities, I'd write them at these arrows.
There are more details we'll cover later, but we've shown what we need to create an HMM by inspection to represent a given signal.
In practice, we expect to have lots of examples of a signal we want to model, and we'll have to create a model that can accommodate all the different examples, balancing both generalization and overfitting. But that will come later. For now, we will assume that we can create an HMM by inspection. In fact, the technique is robust enough that inspection will work for a first pass at a problem.
How about we move on to a real problem?
Sounds like a good idea. We will use sign language recognition as our first application of HMMs. For example, let's consider the signs I and we and create HMMs for each of them. Here's I. We is a little different. Let's focus on the I gesture. We'll use delta Y as our first feature here.
Wait a second. Why don't we use delta X? It looks like it would be easier to differentiate the two words that way, while delta Y is pretty similar for the both of them.
That's right, but I want to show exactly how powerful HMMs can be, so I've purposely chosen a bad feature. We'll actually still be able to tell the difference between the two words by the difference in timing. Let's go through the process and see how that works.
Okay, but sometimes it's hard to visualize the derivative of a signal. Let's have a quiz first to make sure we understand what you're talking about.
Here are several plots of y versus t. Given these plots, match each of the y versus t plots with their derivative plots, delta y versus t. Here's the answer. Okay, I've made an HMM for the sign language word I.
Great. How did you pick those states?
Well, the gesture seemed like it had 3 separate motions, so I made each of those their own state, and chose the transition probabilities based on the timing.
We can take a look at the observed delta Y here to check to see if the model is reasonable. First, the arm comes up towards the chest, and then pauses for a moment, and then goes back down again. We can see that we spend a lot of time in states 1 and 3, so there's a high probability on their self-loops. State 2 is short, so we've given it a smaller probability.
Right. Then we can fill in the output probability distribution similarly. For example, in state 2, we have a high probability of getting a delta Y of 0. We use Gaussians to model the output probabilities here since they have nice properties.
Great. Now here's the HMM I created for the gesture we.
Hold on. I would have used 4 states here. Why did you only use 3?
Well, it was mostly to simplify the problem for our purposes. Note that the middle section varies a little bit more in delta Y than with the middle state of I. And we spend more time in the middle state as well.
I see. It looks like the transition probabilities have changed to reflect this, right?
Correct. We spend longer in that state, so we have a higher probability on the self-loop. Also, we have more variation in the delta Y in this gesture, which leads to a wider and shorter output distribution.
This seems like a good time for a short quiz. What property of the observed sequences of delta Ys can help tell the difference between the two gestures? Probability distributions in respective starting states, probability distributions in middle states, likely time spent in middle states, or none of the above. Select all answers that could apply. Here's the answer. It could be probability distributions in middle states, as well as likely time spent in middle states. So how do we actually go about performing recognition with the models we just created?
Suppose we have a set of observations O that represent the samples in an example we want to recognize. We'll create something called the Viterbi trellis to see how likely each model generated the samples in O. The one that gives us the highest probability will be considered the proper match. However, we don't know the exact sequence of states that created the output. Those are hidden, so we'll need to go through all the possibilities.
That sounds like it would be long, but maybe we can simplify it as we go.
Okay, here's the sequence of delta Ys we collected from the example we want to recognize as I or we.
So our overall goal is to find P of O given lambda I, or the probability of our observation sequence given our model of I.
Correct. Here's how we start the trellis. We have one row for each state in the model. We want to look at which state we're in at each time step.
Well, at the beginning we have to start in state 1, correct?
That's right.
Okay, then at t equal to 2, we can stay in state 1 or transition to state 2, but we can't reach state 3 yet. Looks like we've already eliminated some of this trellis.
Yes, the transition probabilities in these models really limit where you can be at any given time. Perhaps we can have a quiz on that idea.
What state could we be in at t equals to 7? What about t equals 6? Check the boxes on each possible transition. Here's the answer. We know we need to end at state 3. Before that, we could only have been in state 2 or state 3. In the middle of the trellis, it looks like we have many more options. We could really be in any of the 3 states.
That's true. The next thing we need to do is to add the transition probabilities. We can pull those directly from our model, lambda sub I.
Okay, I've added the transition probabilities. That seems simple enough, but how do we go from this to an overall probability?
Here's where our observation sequence comes in. Let's look at time step 1. We saw a delta y of 3, and we know that we can only be in state 1 at that time. By looking at the output distribution at state 1, we can see how probable it is to get a 3 from it. Normally, we would have a real distribution for these outputs, and we could find the actual probability for our output. But for illustration purposes, I'll pick some reasonable numbers. As long as we're consistent, the example should work. I'll call the probability that the Gaussian in the first state generated a delta y of 3 to be 0.5. So let's write that into this node.
I see. So then for time 2, we have an output of 7. 3 was 2 away from state 1's mean of 5, and 7 is also 2 away from 5, so it'll be a probability of 0.5 here as well.
That works. Now we also need to consider state 2, but the probability of getting a 7 there is very small, nearly 0, but not quite. So let's say 10 to the negative 7th.
Why don't we pause for a quiz to make sure this process makes sense? For each of the nodes at t equals to 5, select the answer from these choices that is closest to the output probability. Note that we have filled in the probabilities up to this point to make it easier for you to see what's going on. Here's the answer for t equal to 5. We've also gone ahead and filled in the rest of the trellis. We can follow this process to fill out all the nodes in our trellis.
Now we need to look for the most likely path. At each time frame, we will multiply the transition probability times the output probability. Note that the most likely path may not be the greedy path. In other words, the highest expected value at each transition may not necessarily lead to the highest valued overall path. In this case, the maximum path seems to be this one.
Okay, so let's consider the transition from time 1 to time 2. We can stay in state 1 or move to state 2. What should we use to compare the two options?
The expected value of staying in state 1 is 0.8 times 0.5. Yet, going from state 1 to state 2 is 0.2 times 10 to the negative 7th. The greedy algorithm would expect to stay in state 1 since that value is bigger.
Okay, I see. How does Viterbi account for the overall path?
We need to keep track of the probability of each possible sequence for the trellis. There are only 2 nodes in each sequence so far, so the 2 probabilities are 1 times 0.5 times 0.8 times 0.5, which is equal to 0.2. Or we could have gone down 1 times 0.5 times 0.2 times 10 to the negative 7th, which is equal to 10 to the negative 8th.
It looks like these numbers could get really small.
Yes, in practice we should use log space to calculate these probabilities. Otherwise, we run out of precision in the way the OS represents numbers. But to keep things simple, let's keep going.
Okay. Next, at t equal to 3, our expected values from state 1 are 0.8 times 0.6 and 0.2 times 10 to the negative 5. It looks like we should multiply the previous result, 0.2, by our new expected values.
Right.
We also have to account for the path that went through state 2 earlier. That one will become 10 to the negative 8 times 0.5 times 10 to the negative 5, or 10 to the negative 8 times 0.5 times 10 to the negative 4.
For each state, we're going to keep the path with the maximum value. For state 1, it's going to be this number. For state 2, it's going to be this number. For state 3, it'll be this number. We'll continue this process, keeping track of the maximum path to get to each state, at each time through the trellis. At the end, we choose the most likely path. For this trellis, it turns out to be this one. The final answer for the probability of the observation given our model is about 0.00035. We can then compare this probability to the corresponding result from the trellis for we.
Now it's your turn. Can you tell us the most probable path through the trellis for the model of we? We'll start small. Check the boxes between states to indicate which state transitions can occur. For example, check this box to show that state 2 can transition to state 3. Here's the answer. The transitions through the trellis look like this. Note that this is actually the same as the transitions for the model of I. Now, fill out the transition probabilities for each arrow shown on the trellis, based on the model we created earlier. Here's the answer. Note that the main difference between I and we is the transitions for state 2. In the last quiz, you looked at the transition probabilities. Now, let's consider the output probabilities. We filled out some of the probabilities to get you started. Choose from these answers and fill out the remaining nodes in the trellis. Here's the answer. Finally, we need to determine the most likely sequence through the trellis. Check the boxes to indicate the best path, and then fill out the probability of that path here. Here's the most likely path through the trellis. Notice that it's very similar to the path for I, but the probability is much smaller. So it looks like it's a lot more probable that the model for I generated this data.
Yep, the main difference between the values for the models producing this observation sequence has to do with the middle state. Remember that we use delta y even though it is a relatively bad feature for distinguishing I from we. The output probability Gaussian for the middle state of both models have a mean value of 0. However, with I, the expected probability of getting an actual 0 at the middle state is much higher than with we, a 0.9 versus a 0.7.
Also, with the gesture I, we spend much less time in the middle state than with we. The transition probabilities for the middle states reflect this difference. With I, our transition from the middle state to the last state is 0.5, but with we, it was 0.3. This example shows how well HMMs can distinguish between two gestures, even with relatively poor features.
What is great about HMMs is that the difference in values for even relatively weak features accumulates through time. The longer the gesture is, the easier it is to recognize. Perhaps we can experiment with that idea in a quiz.
Let's look at a new observation sequence. We've replaced the middle 0 observation with a new sequence, -1, 0, and 1. So given these probabilities, can you tell us the probability of this observation sequence given the model for I? Here's the answer. By multiplying all the transition and output probabilities along the Viterbi path in the new trellis, we get the resulting probability for I, 1.42 times 10 to the -5th. Now let's do the same thing for we. We have the same observation sequence as the previous quiz, where the middle 0 was replaced with the sequence -1, 0, and 1. We've given you new probabilities for we, so go ahead and tell us the probability of this observation sequence given our model for we. Here's the resulting probability for we, 2.91 times 10 to the -5th. Note that this answer is higher than what we got for the model of I, indicating that this observation sequence probably came from a we gesture. This is a different result from what we saw previously, showing how the additional time spent in the middle state maps better to our model for we.
When we started this lesson, we created our models by inspection. However, most of the time we want to train using the data itself. When using HMMs for gesture recognition, I like to have at least 12 examples for each gesture I'm trying to recognize. 5 examples at a minimum.
For illustration purposes, let's just use 3 examples of data for the gesture I. Even though it's not the best feature, we're going to continue using delta y for training. The first example is the longest. It has 16 data points.
And I see the next one is really short, with only 5 data points. The last one has 14 time frames. Let's use a 3-state left-to-right topology again for our hidden Markov model. For each of these examples, how are we going to figure out which data goes with which state?
Let's assume all 3 states have about an equal number of frames. I've divided the examples roughly into thirds and drawn a boundary between each third.
On average, our examples are 12 time frames long, so that would mean about 4 data points per state, per example.
Yep, which means our transition probability out of each state is going to be 1/4.
And since the transition probabilities have to sum to 1 for each state, the self-transitions are 3/4.
Now that we've fixed the transition probabilities, let's calculate the output probabilities.
For simplicity, let's use a single Gaussian again. For the first state, we are assigning the 13797 from the first example, and the 2 and 10 from the second example, and the 13787 to this first state. The average of that is approximately 5.4. The standard deviation is, hold on there, let me get out my copy of Octave, about 3.1. Let me draw this under the first state as its output probability.
Since you're being handy, can you do the other states too?
We can calculate the mean value for the second state. This is around negative 0.6 with a standard deviation of 3.1. And the last state has a mean of minus 5 and a standard deviation of about 2.6.
Let's draw those output probabilities as well.
Now we are going to iterate in a process very similar to expectation maximization.
So basically, you set the transition probabilities and calculated the output probabilities based on the assumption that the transition probabilities are correct. Then we're going to assume that the output probabilities are correct and go back and adjust the transition probabilities, and so on until we converge.
So basically, our next step is to see if moving these boundaries in these examples between the states would lead to a better explanation of the data. Basically, we're looking to see if we can get Gaussians with less variance.
Well, that's going to be interesting. Let's look at the first boundary in the first example. Clearly the 5 is closer to the mean of 5.4, so the boundary should move to the right.
But the 2 might still be better in the second state.
How do you justify that?
Well, 2 is 3.4 for the mean of the first state, which is 3.4 over 3.1 standard deviations away. In other words, 2 is a little more than 1 standard deviation away from the first state.
Okay.
But the mean for the second state is minus 0.6, which makes the 2 only 2.6 units away from the mean of the second state, or 2.6 over 3.1 standard deviations away.
Which is less than 1 standard deviation away. So 2 should stay in the second state.
For now.
What do you mean for now?
By the time we finish this iteration, the mean and standard deviations for the states will change, and 2 might move in the first state in the next round.
Okay, but how many of the boundaries change in this iteration?
Let's look. I don't think the negative 1 is going to move from the second state.
But in the second example, this negative 7 is much closer to the mean of the third state, negative 5.
Yep, so let's move the boundary.
Shouldn't we update the means and variances?
It's better to finish looking at the rest of the boundaries first. The last example looks like we have a lot of things we can move.
Right, the 3 should probably move from the second state to the first.
And certainly the minus 5 should go from the second to the third.
How about the negative 3 in the second state?
I have to calculate that one out quick. It's 2.4 over 3.1 standard deviations from the second state, and 2 over 2.6 standard deviations from the mean of the third state. It is slightly closer to the mean of the third state, though not by much.
Great, let's update the boundaries again.
Wow, that's going to cause a big change in our numbers.
Yep, let's recalculate everything.
On average, we now have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 over 3 time frames we expect in the first state. So our transition probability here is going to be 1 over 4.7, or approximately 0.21, making the self-loop 0.79.
The second state has 7 over 3 time frames on average, so the transition probabilities there will be 0.43 and 0.57.
And the last state has 14 over 3 time frames on average, or again, approximately 0.21 transition probability here, and a 0.79 probability here.
Okay, so now we need to update the output probability numbers.
I was afraid you were going to say that. Okay, pulling out Octave again, I get a mean of 5.2 and a standard deviation of 3.0 for the output probability for the first state.
Come on, you're the one with the wearable computer. What's the rest?
Fine. State 2 is easy. It has a mean of 0 and a standard deviation of 1.
Did you do that on purpose?
What?
Make the example so the numbers would come out nice?
I wish I was that smart.
I'm so disillusioned. Okay, what are the values for state 3?
State 3's mean is minus 5 and standard deviation about 2.5.
Great. Now we can do our next iteration.
You mean we gotta do it again?
Don't be a crybaby. It's almost done.
Okay. Well, as I predicted, this 2 is now closer to the first state on this iteration than the second state.
Well, I guess you win that one. is just a little over 1 standard deviation from the mean of the first state, and 2 standard deviations from the mean of the second state.
But the -1 still stays in the second state.
Yep, in both places.
So let's calculate again.
Now, state 1's mean goes to 5, state 2's mean goes slightly negative, and state 3's mean stays the same.
I think we've converged. Let me take a look. Yeah, in the next iteration, none of the boundaries are going to move, nor are the output probabilities going to change.
Does that mean we've successfully trained our HMM for I?
Not yet. Technically speaking, what we've done is use Viterbi alignment to initialize the values for each state of our HMM. In other words, for each time frame in each of our examples, we've assigned a state for that time frame and calculated the resulting averages of all values assigned to each state.
Along with the average amount of time we expect to stay in each state.
Correct.
So what's next?
A process called Baum-Welch re-estimation.
That's like expectation maximization again, right?
Correct.
But how does it differ from what we just did?
It's very similar, but with Baum-Welch, every sample of the data contributes to every state proportionately to the probability of that frame of data being in that state.
Oh, so you're saying that even though this 9 here is most likely in state 1, its value still affects state 2 and 3.
But only a little bit, because its likelihood of belonging to states 2 and 3 is pretty low.
But for data like this 2 here, it has a high likelihood of being in state 1 or state 2.
And thus has a bigger influence on the final output probabilities for those states than for state 3.
Okay, that doesn't sound so bad in theory, but it sounds hard to calculate because you have to weight everything appropriately.
It's actually not that bad. We can use the forward-backward algorithm to help keep track of the calculations. And it's worth the effort because the final model often gives better results than our initial estimate.
Now that we've given the intuition for what is going on, there are several good write-ups on the details of Baum-Welch. Rabiner's tutorial is a classic reference, and Thad's master's thesis has an explanation that continues with the sign language example. Or, just looking at the code to a popular HMM toolkit like HTK can be useful too. In any case, using one of these toolkits and watching the means and variance change as the re-estimation process iterates will help build further intuition, and we highly suggest it.
Now that we've shown how HMMs work, let's provide some more tips on how to improve them.
Okay, in our example of using HMMs to distinguish between the signs I versus we use delta y as a feature. But in reality, delta x would be a better feature.
That's true, but for other signs, delta y would be a good feature. Another good feature is the size of the hand, which helps us get some information as to if the hand is coming towards the camera or away.
Another good feature might be the angle the hand makes to the horizontal.
Since sign language is two-handed, we should have these features both for the right and left hands. Now that we have 8 features we are tracking per time frame, how do we integrate it into our models?
Actually, it's pretty easy. We just add more dimensions for the output probabilities. All our training and recognition work like before. We just have to calculate multi-dimensional distances instead of using just one dimension.
You're right. It gets hard to show in our graphs here, but it's easy enough to code.
What if our output probabilities aren't Gaussian?
Well, according to the central limit theorem, we should get Gaussians if enough factors are affecting the data.
But in practice, sometimes the output probabilities really are not Gaussian. It is not hard for them to be bimodal.
You mean like this?
Yep.
Well, then we can use 2 Gaussians to model it.
Basically using the mixture of Gaussians technique.
Yep, in theory, we can model anything with enough Gaussians. Look at this boxcar distribution.
The more Gaussians we use, the closer we will model it. But how many should we use?
Well, that really depends on your data. Visualization really helps here. In practice, I tend to limit my mixtures to 2 or 3 Gaussians. Otherwise, it tends to overfit.
Next, let's talk about increasing the size of our vocabulary.
Okay, I've selected some signs we can use to start making phrases, but we're going to have to choose topologies for each of them.
Well, we've already chosen topologies for I and we. What sign is next on your list?
Well, let's add want. How many states does that look like to you?
Well, it has the onset where you bring your hands up, the actual motion for the sign itself, and then you're dropping your hands again. I would say 3 states.
Well, how about for need?
That looks similar, so I'd also use 3 states.
Okay, here's a trickier one. This is an example for the sign for table. But hold on, that was actually a poor example. Here's a better example for table.
So your hands go up and down twice? That seems like 4 states in this case.
Yep, but to make things even more interesting, here's another example.
Hold on, that time you went up and down 3 times. How many times is allowed?
Well, generally you'll see the motion repeated twice, But if somebody's thinking hard about what to say, they might repeat the motion stalling for time, sort of like an English speaker saying or
Oh, okay. So how can we deal with that in an HMM?
Well, I didn't say we always had to go from left to right with an HMM.
Oh, okay. So we can actually make a loop in the HMM, say from the third to the second state, so that the motions can be repeated any number of times.
Yep, you got the idea. In practice, we can try lots of different topologies, use cross-validation with randomly selected training and independent test sets to settle on the best one.
Another example of your try the simple thing first strategy?
Exactly, but in this case, let's try the simple topology first and only add states when necessary. Let's look at another issue. Here's an example for cat. And here's another example for cat.
One is one-handed while the other is two-handed. I don't think we're going to solve that with a simple topology trick.
We could try just a normal three-state HMM, and then use a mixture of Gaussians to help handle the funky output probabilities we get.
But I think it makes more sense just to recognize these as two different signs.
Well, how so?
Well, we could train a model for the first variation of sign. We'll call it cat1. Then we'll train a separate model for the second variation and call it cat2. When we recognize either cat1 or cat2, we'll just have our recognizer output cat.
Yep, that should solve the problem. While this approach adds more gestures to our vocabulary, it is often the approach that results in highest accuracy, provided we have enough examples to train all the variations. Now that we have topologies for our 6 signs, let's talk about phrase-level sign language recognition. We have 8 phrases we want to recognize.
Actually, you mean 7 signs and 12 phrases.
Huh?
Since we have 2 variants of cat we are recognizing, expanding all the possibilities leads to 12 phrases.
Good point. To keep things simple, let's use a strict grammar. We will always have a pronoun, followed by a verb, followed by a noun, and we will only recognize one phrase at a time.
So let's expand that out again to be explicit.
Great. Now comes the messy part.
Let's assume we have data from Thad signing that we want to recognize. Here he is actually signing, "I need cat." Really? That's the phrase you came up with for us to use?
Everyone should have a cat.
Okay. Anyway, suppose looking at the delta y feature through time gives us this string of observations.
Which is about 20 samples through time.
We're going to do recognition the same way as before, but with a much bigger trellis.
We have 22 states to worry about. 3 for each of I, we, need, want, cat1 and cat2, and 4 for table.
So where can we be when t is equal to 1?
Well, our grammar says we have to start with I or we. So we have to be in the first state of either of these 2 pronouns.
Where can we be when t equals to 2?
Well, we could stay in the current state, or we could transition into the second state of I or we.
How about t equal to 3?
It's still easy. We can be in states 1 through 3 for I or for we. We haven't had a chance to transition out of the first sign yet.
But what happens with t equal to 4?
Once we get to t equals 4, we could, at least in theory, have transitioned to either of the verbs want or need. We are beginning to see the complexity that will soon overtake us.
That's right, but it's not too bad yet. At t equal to 5, we have more opportunities where we could transition to need or want, but we still can't get to the nouns yet.
At t equals 6, we're still with the pronouns and verbs.
But at t equals to 7, we could possibly transition to table, or cat1, or cat2.
At t equals 8, we could get into the second state of the noun signs. And at t equals 9, we can actually transition into the third state of the noun signs.
At t equals to 10, we have the first time we could transition back from state 3 to state 2 in table. This loop back complicates our trellis a little bit.
But it's not too bad. We just now have this back and forth structure.
And here's the full trellis for after we've taken care of all the data from the example phrase.
Wow, and this was the simplest real example we could come up with. But note here, we couldn't actually reach all these states in the end. We have to get back to the bottom states in one of the 3 nouns.
Yep, this trellis also shows how HMMs can take up a lot of memory.
Imagine if we had a vocabulary that included all 6,000 signs in American Sign Language, or even worse yet, all the variations of those signs that give ASL its expressiveness and speed.
Not to mention what would happen if we were using a real grammar. Which brings up an interesting point. Almost all of language recognizers will have problems keeping the full trellis in memory.
And keeping all the paths updated will also be a problem.
How will we deal with this problem?
We'll use stochastic beam search.
Stochastic beam search? Did we see that before?
Not in detail. So far we've been doing something like a breadth-first search, expanding each possible path at each time step. but now we want to prune some of those paths.
Well, some of those paths are going to get a low probability pretty quickly. For example, staying in the first state of the model for I until t equals 10 seems improbable. We could just drop some of those low probability paths.
Yep, that's the idea of the beam search. But we don't want to get rid of all the low probability paths. It is possible that there is a bad match at the beginning of the phrase that becomes a good match later on. For example, the signer might hesitate or accidentally start with the wrong sign before changing it.
Like someone stuttering or having a false start in a spoken language.
Precisely.
In that case, let's keep the paths randomly in proportion of their probability.
Here are some examples of high probability paths through the trellis, marked in red, and some low probability paths through the trellis, marked in blue.
In that case, let's keep the paths randomly in proportion with their probability.
Yep, the idea has some similarity to the fitness function we talked about with genetic algorithms, or to the randomness in simulated annealing. In practice, it works very well.
Randomness seems to be useful in a lot of AI.
It's a principle I practice in my daily life.
What?
Precisely.
Okay, let's get back to the real topic.
Okay, now let's talk about another trick. When we move from recognizing isolated signs to recognizing phrases of signs, the combination of movements looks very different.
For example, when Thad signed need in isolation, his hand started from a rest position and finished in the rest position. When he signs need in the context of I need cat, the first part of need runs into the last part of I, and the last part of need runs into the first part of cat. His hands are no longer moving so much.
That's right. The signs before and after a given sign can significantly affect how it looks.
So instead of recognizing the 3-state model for need, we're going to concatenate a combined 6-state model of I need and need cat.
In practice, we often have lots of examples of phrases of sign and not individual signs to train on. In my original paper on recognizing phrases of ASL, I had 40 signs in the vocabulary, but the only training data I had was 500 phrases that each contained 5 signs.
In this case, let's suppose we have lots of examples of our 3-sign phrase. In our original example on training an HMM from data, we assumed that the data for an isolated version of the sign for I was evenly divided among its 3 states. We then calculated the output probabilities given that assumption, adjusted the boundaries and transition probabilities, and iterated until convergence.
We're going to do the same thing for our first step here, but this time we'll assume that the data is evenly divided between each sign, and then we'll divide the data for each state in each sign.
And we iterate the same way we did before, adjusting the boundaries on each state and each sign until we converge.
Now's when things get interesting. After we've converged everything for each sign, we're going to go back and find every place where I need occurs. Notice that there will be a lot fewer of those than there are examples of need.
But let's assume that there are enough examples.
Okay, well, we are going to cut out the data we think belongs to I need and train the combined 6-state model on it.
How does that help?
Well, the output probabilities at the boundary between I and need, here and here, as well as the transition probabilities in that region, will be tuned to better represent I need than the general case, which would include we need. In speech, the effect of one phoneme affecting the adjacent phoneme is called coarticulation, and this method of modeling is called context training.
So I assume we're going to do the same thing for need cat 1.
Yep, and for every other 2-sign combination. Need cat 2, want cat 1, want cat 2, I want, we need, and we want. We are going to iterate using Baum-Welch using these larger contexts for embedded training until we converge again.
Why not use 3-sign contexts, or even more when the phrases are complex enough?
If we have enough data, that is not a bad idea because the benefits are actually pretty large. For recognition tasks where there is a language structure, we expect context training to divide our error rate in half. Statistical grammars can help us even more. In our example up to this point, we used a simple grammar of pronoun, verb, and noun, and that placed a strong limit of where we started and ended in our Viterbi trellis.
But in real life, language is not so well segmented. Instead, we can record large amounts of language and determine the fraction of times need follows I versus want following I, or want following we.
We can then use these probabilities to help bias our recognition based on the expected distribution of the co-occurrence of these signs. In practice, using a statistical grammar divides the error rate by another factor of 4. We start with a fundamental error rate of E. When we use context training, we divide in half. And now with statistical grammars, we're dividing it by a factor of 4 again. So basically we end up with our error rate divided by 8. This trick is one of the secret weapons in my research. I look for problems that might have a language-like structure and then apply these techniques to get my error rate down to something reasonable. Another trick is state tying.
You mean combining training for states where the states within the model are close?
Yep, let's look at our models for I and we again. In the case where we are recognizing isolated signs, the initial movement of the right hand going to the chest is very similar in both models. So instead of having an I state 1 and a we state 1, we're just going to have an initial state and define the I and we models such that they both include it. That way, when we are training the HMM, we have twice as much data to train the initial state.
And we can do the same thing with the final state, since the hand going back down to rest looks much the same in the isolated models for I and we.
We have to be careful with this trick because state tying gets more complicated when we start to worry about context training. For I need table and we want cat too, the only states that should be tied are the first state for I and we and the last state for table and cat.
And maybe not even the last states for table and cat too. If we are using more features than just delta y, the end of table and cat 2 could be very different.
Good point. In practice, I often just look for states that seem to have close means and variances during training, and then determine if tying them looks logical given the motion I expect. Again, it's a situation where some visualization of the data and iteration can help us improve our results.
In your past work on gesture recognition, how many dimensions have you used for your output probabilities?
Up to hundreds. At one point, we are creating appearance models of the hand and using a similarity metric of how closely the current hand looked like different visual models of the hand as features for the HMM. However, the problem was there was a lot of noise in that the models that didn't match well were giving relatively random results, causing many of the dimensions to be meaningless unless the hand at that particular time matched well.
So all those dimensions were actually hurting you because they were all very noisy most of the time.
Correct. However, we can use boosting to help us weight the feature vector to combat this problem. This technique is called segmentally boosted HMMs. One of my students, Pei Yin, did his PhD dissertation on the idea, and his results were often 20% better than normal HMMs. For some data sets, we got up to 70% improvement.
How does it work?
First, we align and train the HMMs as normal. Next, we use that training to align the data that belongs to each state as best we can. We examine each state in each model iteratively. We boost by asking which features help us most to differentiate the data for our chosen state versus the rest of the states. We then weight the dimensions appropriately in that HMM. This trick combines some of the advantages of discriminative models with generative models.
Is it in a toolkit somewhere?
Not yet, but I'm thinking about adding it to HTK and our Georgia Tech Gesture Toolkit. Personally, I think it can be pretty powerful, but it is not widely known yet. One last thing I'd like to cover is why the normal HMM formulation is not good for generating data. In the early days of speech recognition, there was the hope that we could use the same HMMs we use to recognize speech to also generate it. It turned out not to be such a good idea, even though later advancements led to good results.
Maybe an example is the best way to show the issue.
You're right. Let's take the same HMM we had at the beginning of the lesson.
The one which modeled the straight lines.
Yep. Now with just looking at the HMM, not the example data, give me 10 numbers that could be generated by the first state.
Okay. -1, -1, -2, -1.5, -1, -1.25, -1.75, and -2.
Now some numbers for the second state.
0, -0.5, -0.25, -0.75, and -1.
Same thing for the third state.
1, 0, 1, 1, 0, 1, 1, 1, 0, 1, 0, 0, 1, 0, 0, 1, 0, 1, 0.
And finally, the last state.
1.5, 1.75, and 1.
Plotting these numbers looks nothing like the original example because the output distributions have no idea of continuity.
How would we fix that?
We could use a lot of states to try to force a better ordering of the output, but that would lead to overfitting. A better idea is to model the state transitions with an HMM, but use a different process while in each state that is more aware of the context to generate the final data. There are several methods that are possible, but the most sophisticated work I know of is by speech synthesis researchers. For example, Google has some good documents of how they are combining HMMs with deep belief networks to get better results.